In the previous lecture, we have discussed about Peterson's solution, which was a software-based solution to the synchronization problem. Now, in this lecture, we'll be discussing about a hardware-based solution to the synchronization problem, which is known as the test and set lock. So first of all, we'll be trying to get a basic idea of how it works. And after that, we'll be going to the underlying details, and we will be seeing how this test and set lock is designed and how it is implemented. Alright, so first let's see basically how it works and what is the main idea behind the test and set lock. So as I already told you, this is a hardware solution to the synchronization problem. And then here the main thing is that there is a shared lock variable which can take either of the two values 0 or 1. So the main thing in this test and set lock is this lock variable, which is a shared variable which is shared between different processes. So this lock variable will have two values which can be either 0 or 1. So if the value is 0 means it is unlocked, and if the value is 1 means it is locked. So if the shared lock variable has the value 0, that means the lock is unlocked, and if it is having the value 1 means it is locked. Now what happens is, before entering into the critical section, a process inquires about the lock. So when a process wants to enter its critical section, what it will do is it will inquire about the lock. It will see whether the lock's value is set to 0 or 1. So it wants to find out whether it is locked or unlocked. So that is the testing part. So let's try to understand the name. So the testing part is what we saw here just now. So when a process wants to enter its critical section, it will inquire if the lock variable is 0 or 1. Now, if it is locked, it keeps on waiting till it becomes free. So when a process wants to enter its critical section, and when it inquires about the lock, and if it finds that the lock value is set to 1, which implies that it is locked, then what will it do? It will keep on waiting until it becomes free. So when the lock value is set to 1, or when it is locked, it implies that some other process is currently executing in its critical section, and so no other processes should be allowed to enter its critical section at that time. So that is what we mean by this lock. So if it is locked, it will have to keep on waiting until it becomes free. And then if it is not locked, it takes the lock and executes the critical section. So if it finds that the lock value is set to 0, that means if it is unlocked, then that process will take the lock and set the lock value to 1. That means that process will set the lock and then it will execute in its critical section. So this is the basic idea. So in a nutshell, we can just say that when a process wants to enter its critical section, it will have to first check the lock, and if the lock is found to be locked, then it has to wait, and if it is unlocked, then it can take the lock and set the lock and then execute in its critical section. So the lock variable is shared between the different processes. It's a shared variable. So let me just take a simple real-life example. Let's say that there is a room which can be used by only one person at a time. So when a person comes, he checks whether the room is locked or unlocked. So if it is unlocked, he can open the room, go inside the room, and he will lock the room from inside and he will do his work. So if another person tries to enter the room at that time, he checks if the room is locked and finds that the room is locked. So he cannot enter at that time. So only when the person who is currently in the room finishes his work and comes out, then only the next person can enter the room when the room is unlocked. So this is the simple concept of this test and set lock. So that is what happens here. Now since we have a basic idea of how it works, we will see the underlying design of this test and set instruction, and we will be seeing how it is implemented when processes tries to enter in their critical section. So here we have the definition of the test and set instruction. So this test and set instruction is nothing but a function, and this function has a Boolean return type. So Boolean return type means this function will return a variable which is of Boolean data type. So what is a Boolean? Like for example 0 or 1 or true or false and so on. So that is a return type of this function, and also this function takes a Boolean variable as an argument. So the argument that is taken by this function, that is this target variable, is also a Boolean data type. So this target variable will signify the log variable. So we said that there is going to be a shared log variable. So this log variable's value will be passed to this target variable over here. So it will have either 0 or 1 as a value. And now inside this function what happens, we are having another variable called RV, which is also of Boolean type, and then we are storing the target's value to this RV. So if target value is 0, then RV value will also be 0. If target value is 1, RV value also will be 1. And after that, we are setting the target value back to true again, and then we are returning the value of RV. So whatever is passed to this function, that is this target variable, will be the one that is going to be returned. Why is that? Because that target variable is stored into RV, and that exact thing is what is going to be returned. Alright, so this is what happens. And then here I have written something called atomic operation. So what do we mean by this? I have written this atomic operation because in this test and set log instruction, whatever is happening in a process, that is when a process checks for the log, and if the log is available, and when it acquires a log and sets the log value to 1 and executes in its critical section, all these tasks will happen as a single operation which cannot be interrupted by anyone. So that is what we mean by atomic operation. It is a single operation and is passed to this function. That because that target variable is stored into RV, and that exact thing is what is going to be returned. Alright, so this is what happens. And then here I have written something called atomic operation. So what do we mean by this? I have written this atomic operation because in this test and set log instruction, whatever is happening in a process, that is when a process checks for the log, and if the log is available, and when it acquires a log and sets the log value to 1 and executes in its critical section, all these tasks will happen as a single operation which cannot be interrupted by anyone. So that is what we mean by atomic operation. It is a single operation that will be uninterrupted. So keep in mind that whatever is happening in this test and set log, when a process acquires the log and executes in its critical section, it will be happening as an atomic operation. Alright, so keep that in mind. And here we have seen the definition of the test and set instruction. And now let us see when a process wants to enter this critical section, how does this work? Alright, here we have the structure of a process which we will call process P1, which wants to enter its critical section. So here we are going to make use of the test and set lock in order to achieve process synchronization. Alright, so let's see. So this process P1, it wants to enter its critical section. So what it will do, it will come to this do while loop. So in this do while loop, we have the test and set function, and then the lock variable is passed to the function. Okay, so when this process P1 wants to enter its critical section, it will come to this do while loop, and in this do while loop, what are we having in this while condition? Let's see. Inside this while loop, we are having the test and set function, which is this function, and then we are passing as an argument the lock. So the lock variable will always be set to 0 in the beginning. So keep in mind that the lock value is always 0 initially. So here we see that we are actually passing the address of the lock, ampersand lock, and here we are actually using a pointer variable. So we are using this in this way because, as I told you, this lock variable is shared between different processes. So we need to have the current value of this lock every time a process accesses this lock variable. That is why we are making use of this address and pointer and all. So you don't have to get confused going to the detail of the code. Just understand that this is a shared variable. That is why we are going to make use of the address and pointer and all that. So for simplicity, just remember that it is a shared variable and we are going to treat it as a normal variable. Okay, so let's see. As I told you, the lock's value is set to 0 always in the beginning. So when process P1 wants to enter its critical section, assuming that this is the beginning, the lock's value is 0. So we have test and set, and instead of lock we have 0. So test and set of 0 is called. Now where is test and set? This is the definition of test and set. And we have a boolean target here. So whatever is passed from here will be stored in this target. So here we passed 0. So the target's value will be 0. Now what will happen? We come into this function and we have a boolean RV, and it is equal to the target. That means whatever value is there in target, we are storing it to this RV. So what is target? It is 0. We got that 0 from here. So this value of target is 0 now. So target's value is stored to RV. So RV's value also is now 0. And then the target value is set back to true again. Target is equal to true, and then return RV. So what is RV? RV is 0, I told you. So RV is going to be returned. That means 0 is going to be returned. So this whole function is going to return the value 0. So when we call the function here, passing the value 0, 0 is returned. So the result of this entire function will be 0. So it is like while 0. This whole thing becomes 0. Now look at this while loop again. There is a semicolon here. That means there are no instructions inside this while loop. We are only having the condition, and as long as the condition is true, the control will remain inside this while and it will continue looping inside this while loop as long as the condition is true. And when the condition becomes false, it will break out of the while loop and come to the remaining part. Now here, as I told you, the return value was RV, which is 0, so it becomes while 0. So keep another thing in mind. In the while loop, when we are having the value 1, that means the while condition is true, and when we are having the value 0, the while condition will become false. Okay, that is the concept of while loop. So here we know that 0 was returned, so it becomes while of 0. So while of 0 means what? While condition becomes false. So when while condition becomes false, it will break out of this while loop and it will come to the critical section. So it comes to the critical section and it will execute in its critical section. So why is it able to execute in its critical section? Because the lock value was initially set to 0. So 0 implies that no processes are currently executing in their critical sections. So that is why this while loop was able to break and it came to the critical section and it is executing in its critical section. And while it is executing in its critical section, what is the current value of lock at that time? That also we need to keep in mind. So we see that lock and target, as I told you, is going to be the same thing. So target value, if you look here, was set to true. So after this log became false and enters this critical section, just at that time, the target value is also set to true. That means the log's value is again set to 1. So while it is executing in this critical section, the log's value is currently 1. And at that time, no other process can enter the critical section. So after the critical section of this process P1 is completed, then it will again set the log value as false, and then it will execute the remainder section. So when it sets the log value as false, at this point of time, if there are any other process that wants to enter its critical section, then they will be allowed to enter their critical section because the log is now set to false. Alright, so this is how it works in process P1. Now let's go a little backward, and let's say that there is another process P2 that tries to enter its critical section when P1 was actually already executing in its critical section. So here we have a process P2 that tries to execute its critical section. So it will also do the same. same thing. So it has its own while loop, and it is going to call the test and set instruction with the value of the lock. Now here is the most important thing. What is the value of the lock now? I told you the lock's value is set to 1. When it is executing in its critical section here, we already set the target equal to true, and after that only we broke from the loop and came to the critical section. So the target's value is true means the lock's value is 1. So here the lock's value that will be passed will be 1. So it says test and set of 1. So when test and set of 1 is called, what will happen? 1 will be passed to this target variable. Now when 1 is passed to the target variable, what happens? RV is equal to target. That means RV also will be equal to 1. Then target is set to true, and then return RV. So what is RV? RV's value is 1. So 1 is going to be returned in this function. So here 1 is going to be returned when this function is called. So it is going to be while of 1. This entire thing becomes 1. And as I told you, in while loop, when the condition is 1, that means the while condition is true. And when the while condition is true, it will keep looping inside the while loop, and it will not come out of the while loop because of this semicolon. So since it is 1, it will stay inside this while loop, and it will do nothing but just keep looping inside the while loop, and it will not come to this critical section part. So we see that when P1 is executing in its critical section, even though P2 tried to enter the critical section, it cannot enter its critical section because of the way it is designed. Alright, now let's say that P1 completed its execution of critical section, and at that time it will set the log value as false or 0. Now when the log value is set to 0, what happens? If P2 is still trying to execute in its critical section, so here the log value now becomes 0 because it is set to false here. So false and 0 same thing. So it is set to 0, so it becomes becomes 0, and when test and set of 0 is called, we know what will happen here. Target becomes 0, and RV is equal to target means RV is equal to 0. Then target is set to true, and RV is returned, which is 0. So 0 gets returned over here. So this whole value becomes 0, and when the whole value becomes 0, what happens? The while condition becomes false. And when while condition becomes false, it will break out of the while loop, and it will come to the critical section, and it will execute in its critical section. Now when this is also executing in its critical section, remember that the target is set to true. So the lock is set to 1 again, and any other process that tries to enter its critical section will not be allowed because of that. And then after this P2 completes its critical section, it will set the log value as false again, allowing other processes to enter their critical sections, and then it will execute the remainder section. So this is how the test and set lock works. So we see that when the lock's value is 0, then the process is allowed to enter its critical section and do its execution, and while it is executing in its critical section, the log value is set to 1, hence not allowing any other processes to enter their critical sections until and unless the current process finishes its execution in its critical section. So that is how the test and set lock is implemented. So keep in mind that this log variable is shared, and this is an atomic operation. That means all these things happen as one uninterruptible operation. Alright, so this is a hardware-based solution to the synchronization problem. And now we have the question if this is the best solution, or does this solution also have any flaws? So let's find out. Now the advantage of this solution is that it satisfies the mutual exclusion. So it satisfies mutual exclusion. I don't need to explain it. We have seen it very clearly that when one process is executing in its critical section, the other process is not allowed to enter its critical section. So mutual exclusion is satisfied, but it does not satisfy the bounded waiting. So why is the bounded waiting condition not satisfied? So let's say that P1 was executing in its critical section, so P2 tries to execute in its critical section but was not allowed because lock was set to 1. And then let's say that P2 was trying to execute for some more time, but somehow it got preempted, and at that time another process P3 arrived. Now P3 also is trying to enter its critical section, and then it was not able to enter because P1 was already executing. And let's say that at that point of time P1 completes its critical section and sets the lock as false. Now P3 is requesting for the critical section, so as it is the one requesting right now, it will get hold of the lock and it will be able to enter its critical section. So this P2, which is the unlucky process that went away, when it tries to come back and execute in its critical section, it finds that P3 is now executing in its critical section. So again, it may try for some time and it may get preempted, and let's say that again the next time it comes back, it finds that some other process is already executing in its critical section. So this is a possibility that can happen. There could be some unlucky processes like that which are not getting the chance to enter their critical section, and hence it leads to starvation of that process from its critical section. Disadvantage of this test and set lock. So other than that, it satisfies a mutual exclusion condition, and this is a hardware based solution to the synchronization problem. So that is how the test and set lock works, and I hope its implementation and the way it is designed is clear to you. Thank you for watching and see you in the next one. or the section and section. So analytical section when P1 was actually value is true means
Hi. The topic is Huffman coding. Huffman coding is a compression technique. It is used for reducing the size of data or message. Suppose you want to store the data in a file, so you can store the data in compressed form to reduce the size of a file. When the data is sent over a network, data can be compressed and sent to reduce the cost of transmission. In this video, I am going to explain you if a normal message is sent, what will be the cost, and what is the fixed size encoding, then what is variable size encoding, that is Huffman coding. Now let us study the problem. I have a message here. Now this message I want to store it in a file, or I want to send it over a network. Then let us understand what will be the cost of a message. So the cost of this message, or the size of the message, will be measured in terms of bits. Let us check. First of all, there are 20 letters in this one. So the length of this message is 20. Next, how this message has to be sent? It has to be sent by using ASCII code. Electronic devices or computers all use ASCII codes for characters or English alphabet. So these are all characters. ASCII codes are 8 bits. I have used alphabets A to E here, so that is easy to understand for us. So if I say A, its ASCII code is 65 and the binary form is this one. So total 8 bits, these are 8 bits that are representing decimal 65, and that is representing A. Similarly, if I say B, then it is 66. This will be for 66. Likewise, C, D, E. For everyone we have, there is a 67 and 68 and 69, and here the binary code will be there. So 8 bits are there for each alphabet. Now if normally this message is sent 8 bits for each alphabet, then total number of bits will be how much? As there are 20 alphabets in this message, so this will be 8 into 20, that is 160 bits. Size of the message will be 160 bits. Now this is the simple message sent without encoding. The size will be 160 bits. 8 bit for each alphabet. Now let us look at, can we use our own codes instead of ASCII codes? How it is possible? See, I am not using all English alphabets or all possible symbols on the keyboard. I am not using every symbol from the character set. I am using only 5 alphabets, that too capital letters. Then, do I need 8 codes, 8-bit codes for representing just 5 alphabets? No, few bits are sufficient. So can I use my own codes with less amount of bits? Yes. So next we will see fixed size codes. Here I have taken alphabets in this message, and how many times each alphabet is appearing, I have written the count here, or you can also call it as frequency. A is appearing 3 times, 1, 2, 3. Likewise, you can check all, how many times they are appearing, I have written them here. Total there are 20 alphabets. If you want to see the frequency, then you can say this is 3 by 20, that is 3 by 20, or this is 5 by 20, because total number are 20, so this is 6 by 20, and you can take the ratios. I prefer taking counts, that is easy for working. Even what should be the code? See, I have 5 characters. I don't need 8 bits for just 5 characters. Less amount of bits? Yes. So next we will see fixed size codes. Here I have taken alphabets in this message, and how many times each alphabet is appearing, I have written the count here, or you can also call it as frequency. A is appearing 3 times, 1, 2, 3. Likewise, you can check all, how many times they are appearing. I have written them here. Total there are 20 alphabets. If you want to see the frequency, then you can say this is 3 by 20, that is 3 by 20, or this is 5 by 20, because total number are 20, so this is 6 by 20, and you can take the ratios. I prefer taking counts, that is easy for working. Even what should be the code? See, I have 5 characters. I don't need 8 bits for just 5 characters. 8-bit ASCII codes are for 128 characters or 128 symbols. But for only 5, let us see. If I have just one bit, then either I can write 0 or 1. So how many symbols I can represent? How many characters? Only 2 characters. If I have 2 bits, then how many I can represent? I can write 0, 0, 0, 1, 1, 0, 1, 1. So I can have 4 different combinations, and each combination can represent one symbol. But I have 5, so for that I can take 3 bits. So in this, how many combinations are possible? 0 to 7, that is 8 combinations are possible. So I will take 5 out of that. So let us say in 3 bits I will say A is 0, 0, 0, B is 0, 0, 1, C is 0, 1, 0, D is 0, 1, 1, and E is 1, 0, 0. I have given my own 3-bit codes. I will use this for encoding this message, and this will reduce the size of the message. So it means here, instead of writing ASCII code, I will be writing 001 for B and 010 for C. Likewise, go on. When the message is encoded using this one, then what will be the size of the message? As we know well that there are 20 characters and each takes 3 bits. So this will be 60 bits. So size of the message will be 60 bits. And one more important thing we cannot neglect. What is that? When I am sending a message, suppose encoded in this one, now how the receiver will know what are the codes? Even if I store it in a file and then later I want to retrieve, how do I remember what are the codes used? 00 means A only, is it? See, for making it easy, I have taken the alphabets A to E here. The alphabets can be anything. This can be A, this can be M, this can be O, this can be Q. Then how I can know which code is for what? So I should also have the codes, that's this table also along with the message. So this is an encoded message and this is the table. Use this table to decode the message. Yes. So message is 60-bit. Then you need the table also, the chart of codes that will help to decode this message. So let us see, you have to send this one also. How how much size this will take. See, I have 5 alphabets. This alphabet should be in original form now. Now standard is what? ASCII code. So I must write ASCII code of all these. ASCII code of all these. So for this 8 bits. So total how many? 5. So 5 into 8 bits. This is for what? Characters or symbols. Then for each 3-bit code, for A this is the code, B this is the code, for everything I should also have the code. So total how many? 5. And how many bits for each code? 3. So this is for codes. So this makes how much? This is 40 plus 15. This is 55. And what is the size of this original message? So message is 60 bits, right? And table or a chart of codes is 55 bits. So total how much this will be? 115 bits. Yes. So total size of the message along with the chart is 115 bits. It's not just 60 bits, it is 115 bits. No doubt the size of the message is reduced, but table is also important. So it was 160, now it became 115. So around 35 to 40% of reduction in size from 160 to 115. Right? So this is one method with fixed size codes. Now we'll go to variable size code and let us follow Huffman coding, which will still reduce the size of the message. Huffman encoding. Huffman says that we don't have to say take fixed size codes for the alphabets. Some characters or alphabets may be appearing few times, less number of times, and few may be appearing more number of times. So if you give small size code for the more appearing characters, then the size of the entire message will be definitely reduced. Appear method with fixed size codes. Now we'll go to variable size code and let us follow Huffman coding, which will still reduce the size of the message. Huffman encoding. Huffman says that we don't have to say take fixed size codes for the alphabets. Some characters or alphabets may be appearing few times, less number of times, and few may be appearing more number of times. So if you give small size code for the more appearing characters, then the size of the entire message will be definitely reduced. So let us see what is his idea. Already we have this table, all the alphabets and how many times they are appearing in a message. So that gives the frequency of those alphabets. Now Huffman code follows optimal merge pattern. Now we have to generate our own code. So what should be the method for the code? So Huffman has given an approach for getting our own variable size codes. So he says that all those alphabets should be arranged in the increasing order of their count. So this is the least one and this is the next one and next one and so on. So they are arranged in the increasing order of their count or frequencies. So the first, the smallest one, then the highest one. So this optimal merge pattern should be followed on this one. So what I should do, merge two smallest one and make one node. So this is 2 plus 3, this is 5. Now next select two smallest and form a node. So 5, 4, 5, 6, these are remaining. Out of this, which are two smaller? Either I can take this 5, 4 or that 5, 4. So I will take this one. So I'll combine this one with this. So this is 9. Now what are the list I have or the nodes I have? 9, 5, 6, these are the two minimum. So combine these two. This is lamb. Then combine these two. Two are remaining now. So this one and this one. So this gives what? 20. So here we got a optimal merge pattern tree. So actually we followed optimal merge pattern, that is greedy approach. Always select two, minimum one, and we got this one. Now this tree will help us define the codes. How? On the left hand side edges, mark them as zeros, and on the right hand side edges, mark them as 1. That's it. Now what are the codes? For each alphabet, follow a path from root onwards. So for A, what is the code? 0, 0, 1. So A is 0, 0, 1. Then B is 1, 0, 1, 0. C 1, 1, 1, 1. D 0, 1, 0, 1. And E 0, 0, 0. 0, 0, 0. That's it. These are the new codes we have. Now you can see some code is of 3 bits and one code is of 2 bits, like that. So even we may have the codes with 1 bit also. Not here, in some examples. So variable size codes are there. Now I can use these codes for encoding my message. Like B is 1, 0. C is how much? 1, 1. C is 1, 1. And A is 0, 0, 1. B is 1, 0. B is 1, 0. And D is 0, 1, 0, 1. Go on. If I use these codes, what will be the size of my message? So for that, how many bits are there for A? 3 bits. And how many times A is appearing? This is 3 into 3, 9. And 2 bits, and this appearing for 5 times. So 5 into 2, 10. 2 bits, 1, 1, appearing for 6 times. So 6 into 2, 12. 2 bits appearing for 4 times. So 4 into 2, 8. And 3 bits appearing for 2 times. So 2 into 3 is 6. So For entire message, I have how many times each character is appearing and their sizes of codes I have taken, and I got this one. Now total number of bits and their accuracy 3, 4 into 2, 8. and 3 bits appearing for 2 times. So 2 into 3 is 6. So for entire message I have how many times each character is appearing and their sizes of codes I have taken, and I got this one. Now total number of bits are 45 bits. Size of the message is 45 bits, means if I encode all, I just need 45 bits. So the message size is 45 bits. Now one more thing we should consider. Along with the message, I should also send this chart or a table or a tree. Then only decoding can be done. Means along with the encoded message, what are the codes used, that should also be there. Then only decoding can be done. So somehow this tree should be preserved or the table should be preserved. Or you can see what will be the size of the table. All these alphabets I should send their ASCII codes, the standard code. So 8 bit of ASCII code. How many alphabets are there? 5. So this makes how many? 40 bits. Then codes also I should send. So these codes, when they are stored, so how many codes are there? 5 codes, but what are the number of bits? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is forming 12 bits. So together, this 40 plus that 12, so 52 bits are required for tree or a table. Tree or table. So what is the total size? Message is 45 bits and the table or a tree is 52 bits, and this will be 97 bits. Yes, now you can see that it is still reduced from fixed size codes. So that's all about Huffman coding. Now if you want to know the size of the message, that 45, you can know it from the tree also. How? See, this is the distance. How much is the distance? 1, 2, 3, and frequency is what? 2. So 3 into 2. So distance into frequency of each or count of each. You can take sigma, sum of all these. So this will be distance is 3 and frequency is 2, plus distance is 3 and frequency is 3, plus distance is 2 and the frequency is 4. Distance is 2, frequency 5. And distance is 2 and frequency is 6. So this is nothing but this calculation that we got, and this will be 45 bits only. So if you want to know what will be the size of the entire message, from the tree also you can find out by using this formula. If you refer a video on optimal merge pattern, you find that formula is defined. Let us see how decoding is done. Huffman encoding. Huffman says that we don't have to take fixed size codes for the alphabets. Some characters or alphabets may be appearing few times, less number of times, and few may be appearing more number of times. So if you give small size code for the more appearing characters, then the size of the entire message will be definitely reduced. and the frequency is 4. See, this is the distance. How much is the distance? 1, 2, 3. All these alphabets, I should send their ASCII codes, the standard code. So 8 bit of ASCII code. How many alphabets are there? 5. So this makes how many? 40 bits. Then codes also I should send. So these codes, when they are stored, so how many codes are there? 5 codes, but what are the number of bits? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is forming 12 bits. So together, this 40 plus that 12, so 52 bits are required for tree or a table. Tree or table. So what is the total size? Message is 45 bits and a table or a tree is 52 bits. And this will be 97 bits. Yes. The size of the message, that 45, you can know it from the tree also. How? See, this is the distance. How much is the distance? 1, 2, 3. And frequency is what? 2. So 3 into 2. So distance, let us see how decoding is done. And distance is 2 and frequency is 6. So this is nothing but this calculation that we got, and this will be 45 bits only. So if you want to know what will be the size of the entire message from the tree also, you can find out by using this formula.